Welcome to my talk on strategy synthesis for partially known switched stochastic systems. My name is John Jackson. I am a PhD student at CU Boulder, and I did this work in conjunction with Professor Laurenti at TU Delft and Professors Frew and Lahijanian also at CU Boulder. Let's get started. As autonomous systems are becoming more complex, generating control strategies for them is becoming more of a challenge, and even more so if there are unmodeled components of the dynamics. Consider this small unmanned aircraft system flying in an urban environment, and its mission is to go to drop point 1, drop off a package, and go to drop point 2 and drop off a package. And we can state this mission as going to these drop points and also avoiding all of the restricted zones and all of the other vehicles that might be in the environment. Now, under some control action, the aircraft might end up in a region with some uncertainty and still accomplish its mission. But as we're trying to reason about the aircraft accomplishing this mission overall, trying to plan farther and farther into the future becomes very challenging as these uncertainties tend to propagate, and we can't make any rigorous statements about how the aircraft will accomplish its mission. And this is a big deal as a lot of autonomous systems are operating around humans in busy environments, and the last thing we want is for systems to fail and for us to lose systems, cause property damage, and even harm humans. Stated a little more formally, the problem can be stated as a discrete time optimal control problem. In our case, we're looking at a system of this form where this F component consists of any part of the dynamics that are known, and G consists of any unmodeled dynamics. Now, as we're dealing with stochastic systems, we're looking at sub-Gaussian noise distributions, which lets us lift the often restrictive Gaussian assumption. We also assume that control actions can be drawn from this finite set of controllers, which can be thought of as feedback controls or other symbolic control symbols. So in lieu of knowing what this G is, we are instead given a data set that's generated by the system, and also we're given some continuity assumptions on this unknown dynamic portion. And the mission, as stated before, is go to goal 1 and go to goal 2, and always avoid restricted airspace. This is readily expressed as a linear temporal logic interpreted over finite traces specification, which I'll refer to as phi. This relatively new class of logical specifications is really appropriate for the types of missions that we're considering here, going to a region and another region while always trying to avoid certain parts of the state space. So what we want to find is a strategy pi that maps from system paths to control actions in order to accomplish this mission. And we assume that there exists some unknown oracle policy pi star, such that the probability of satisfying this mission specification from an initial state is maximized, and this value is pi star. Now, we don't know this because we don't know the dynamics, but our problem can be boiled down to synthesizing a switching strategy that chooses between these different controller actions for this partially known system as close to this true optimal strategy as possible. Now, as we want to generate rigorous guarantees on the strategy that we come up with, we use a class of formal method tools known as abstraction-based synthesis. Now, at a high level, what this is a procedure to take this system model, which may exist in continuous state space and even over continuous action spaces, and discretize it to construct this finite state abstraction, such as a Markov decision process. Given a structure of this form and a mission specification, we can run a synthesis algorithm that comes up with a strategy on this finite state machine with associated guarantees of either satisfying or violating the mission specification. Now, because we started with this complete system model, if we apply this strategy, the guarantees carry over to the system model. However, we're not starting from this assumption. We're starting from having less information, such as having a partial model. Now, given this partial knowledge, we can run this same abstraction-based approach and get guarantees. However, these guarantees no longer extend and apply to the underlying system model. And on top of this partial knowledge, we might have learned components from data, where even though our overall system starts to look like the system model, we still can't formally bring these guarantees to the system model. So the challenges we address in this work are, first off, with this partial model and learned model, how can we construct an abstraction that effectively simulates this? And also, once we have this abstraction, how can we generate a strategy whose guarantees will extend to the underlying system model? Using the data that a system generates in order to verify its behaviors takes many forms. Some related work includes trying to verify system behavior by learning systems that are assumed to have a linear structure to them. And extending this to the nonlinear case has involved looking at polynomial approximations of potentially nonlinear dynamics. But using polynomial expressions, it's hard to extend guarantees to the underlying system directly. Gaussian process regression has become very popular due to its powerful predictive and learning of unknown functions, and it has been incorporated in, for example, safe learning and reinforcement learning on safe sets, and incorporated with control barrier certificates to synthesize control strategies. Now, some open questions related to these include, first, including a formal specification in terms of doing safe reinforcement learning, and then also trying to ensure completeness, or if a strategy exists, trying to make sure that one is returned. So in order to overcome these problems, we're proposing a data-driven abstraction-based strategy synthesis approach for switch stochastic systems that have guarantees that extend to the underlying system. Let's start with a high-level overview of our framework. Given our unknown system, it generates a data set that we can use for Gaussian process regression. This lets us learn the unknown components of the dynamics and gives us a qualitative error results on the quality of the regression. We use this as a basis to construct our abstraction in the form of an interval Markov decision process. This abstraction captures all the possible behaviors of our unknown system. As I mentioned previously, our mission specification is given by an LTLF, or linear temporal logic over finite traces logic, and this can be expressed as a deterministic finite automaton. We take the product between this IMDP and the DFA in order to come up with the so-called product IMDP. This abstraction now embeds the behavior of the system as it relates to the mission specification, and on this we can do strategy synthesis. Now, this strategy comes with its own guarantees, and we show that these guarantees extend to the latent system. So now, starting from Gaussian process regression, I'll talk about each one of these components in a little bit more detail. Gaussian process regression is a popular way to learn an unknown function from a noisy data set that it's generated. Given the structure of our discrete time system, we can take our data set, which consists of states xk plus 1, the previous state xk, and the choice of control input, and come up with effectively noisy measurements of the unknown dynamics. Now, the standard procedure this follows is assuming that this unknown portion is distributed according to a prior mean and covariance function, doing Bayesian conditioning to come up with a maximum likelihood estimate G hat. Now, because we're using non-Gaussian noise and we're interested in a little more general probabilistic error, we use the so-called reproducing kernel Hilbert space assumption. And specifically, we're using a result from Chowdhury. And these assumptions really got their root in the multi-arm bandit regret analysis, where we are trying to learn a function and trying to minimize this uncertainty as fast as we can. So using this assumption, we can lift the Gaussian noise assumption and instead say that this unknown function lies in the span of the prior of this covariance function. Without going into too much detail, what this lets us do is use a general probabilistic error bounds using GP regression, and it takes this form where we can say the distance of G and its estimate G hat is less than some epsilon term, which depends on a host of things like the RKHS norm of the unknown function and the information gain term, and associating it with this 1 minus delta probability. And this holds for some bounded part of the state space X. Like I mentioned before, we use this Gaussian process regression to come up with an abstraction. And here I'll walk you through how we perform this type of abstraction. So given our toy example, we have a bounded subset of the state space. And the first thing that we do is, according to the labels that are in our state space, we perform a discretization, shown by this grid here. Now, this discretization doesn't need to be this uniform grid cell here. This is just a simple demonstration, but we do need this discretization to respect whatever labels that we have here. For example, this Q prime state, all of the states within it have the label RA, so Q prime itself has label RA. And in addition, we have another general state that is considered unsafe or out of bounds that just captures everything that might be outside of this bounded state space. Once we have this discretization of our state space, the next challenge is to come up with the transition relation between a starting state Q and a target state Q prime. Ideally, we'd like to calculate this probability of transition directly. However, this is typically intractable because each state Q contains an infinite number of states and the dynamics are nonlinear in general. So let's think about all of the sources of uncertainty that we have in our problem. First, we have the process noise, which we assume to know the distribution. This is parameterized by eta and with an associated probability of the process noise being within a ball of radius eta. Next, we have the learning error, which we parameterize by epsilon, and likewise, we can come up with a probability of the unknown dynamics and our learned dynamics being epsilon close. And finally, due to this discretization, we introduce some additional error that we need to account for. Now, since we can't come up with this probability directly, we resign to coming up with lower bounds of transitioning and upper bounds of transitioning between Q and Q prime. To come up with these lower and upper bounds, we first start with the law of total probability, where if we condition out the learning error parameterized by epsilon, we can look at the probability of transitioning from Q to Q prime, given our dynamics are epsilon close, and likewise the transition probability, given that our dynamics are not epsilon close. We use this as a basis for calculating the lower bound and upper bound transitions here, but here I will just discuss how we come about with this upper bound of transitioning. So we first look at this first term and realize that if we can find a point X in Q that can upper bound this first term, we can upper bound the transition probability. This second term of transitioning the Q to Q prime when the dynamics are not epsilon close is more difficult to deal with, so we simply upper bound this term by 1. And we note that this probability of not being epsilon close is simply the complementary probability of being epsilon close. So now, as I mentioned previously, there are an infinite number of states in Q, so it's infeasible to check them all. So we simplify this problem by simply looking at the image of Q under the learned dynamics and an expanded version of our target set Q prime that takes into account the learning error and the noise term being epsilon close. So if we expand Q prime by these parameters epsilon and eta and compare this to the learned image of Q, we can finally come up with an upper bound that depends on just checking the intersection of the learned dynamics with the expanded version of Q prime. Now, if these two sets do intersect, then the upper bound of the probability is calculated just like this, where we can account for the learning error and the process noise probability. And if the two sets do not intersect, this maximum term goes to 0, and we're left with this 1 minus p epsilon term. And the trick here is to try to find an epsilon large enough that either an intersection exists or this second term is driven to 0. So this was a high-level overview of how we calculate the upper bound of transitioning from Q to Q prime. And calculating this lower bound is very similar, except we look at a shrinkage of Q prime by, again, epsilon and eta. Now that we have a way to calculate upper and lower bounds of the probability of transitioning from Q to Q prime, we can now finally construct our abstraction. So for every pair of discrete states that we get from our discretization of our state space, we can compute under each action the lower bound and upper bound of transitioning to that state. Now for each one of these states as well, there is an associated label that comes from the encompassing states of the state space. So now what we have is this interval Markov decision process that defines an entire space of Markov decision processes using these transition probability intervals. This IMDP abstraction simulates all possible behaviors of our system. So now the next step is to take this abstraction and somehow incorporate the dependence of our specification. As I mentioned previously, we're using linear temporal logic over finite traces, or LTLF, to specify our system behavior. LTLF is a regular language with the same syntax as LTL, but its syntax is interpreted over finite traces. So while we lose the ability to express infinite behaviors for our system, practically that doesn't make a difference for us. As it's a regular language, we can use the deterministic finite automaton, or DFA, associated with the specification phi in order to track our progress towards its satisfaction. As an example, consider the specification globally not C, eventually A, and eventually B. The DFA associated with this is a finite state machine that we can use to track our progress. If we reach the sync state associated with this, we violate the specification. Likewise, if we reach the accepting state, this is equivalent to satisfying the specification. We can use this DFA as a basis to incorporate specification progress in our abstraction. Starting with this DFA expression of our specification, we can take the product of it with our IMDP abstraction of our system behavior to get the resultant product IMDP. This is a large structure consisting of a Cartesian product of all of the different pairs of states between the DFA and original IMDP. And these transition intervals come about from the original IMDP and the allowed symbolic transitions in the DFA. Now, more detail can be found in the paper on this, but the crucial part is that this structure here itself is an IMDP that we can reason over, and the paths of this IMDP now simulate the system behavior, but it simulates it such that it's taking to our mission specification into account. And reaching and accepting states in this product IMDP means the system has satisfied the mission specification, and likewise reaching this sync state shown here means that our system is violating the specification. Now that we have an abstraction of our system that captures our system behavior and progress towards satisfying the specification, our final task is to synthesize a strategy on this IMDP. We can do this by modeling this synthesis problem as a two-player game, where us as player one tries to choose actions that drive us towards the accepting state in the IMDP, and our adversary chooses feasible transition probability distributions under each action. So as we iterate over actions and our adversary chooses transition distributions, our goal is to come up with an optimal robust strategy that chooses actions that accounts for the worst possible transition probabilities that our adversary may choose. This can be posed as this min-max problem over different strategies and transition distributions. And the lower bound of satisfaction is given by the lower bound of satisfying or reaching and accepting state in the IMDP from some arbitrary initial state S0. And likewise, we can calculate the upper bound of satisfying the specification by assuming that the adversary is helping us reach the accepting state. This max-min and max-max problem is readily posed as a value iteration problem over these strategies and transition distributions that is guaranteed to converge in finite time and return a policy, pi. Once we have this robust policy, we can then start to reason about its optimality with respect to the true underlying system and the best policy that we could possibly find. So here we have the 0-1 axis with a 95% line here, and we have the lower bound and upper bound of satisfying the specification given some policy synthesized on the IMDP. By construction, we know that the true probability of satisfaction given the unknown best policy lies within this interval of PL and PU. So automatically, by looking at PL, we get a bound on the error between the optimal unknown policy and the policy we have on the IMDP. So we can start to think about guarantees by looking at first the lower bound. If we want to ask, is this lower bound greater than 95%, we simply look at this interval and we can make a guarantee on that. And by extension, we have a guarantee on where the unknown underlying probability of satisfaction lies. Likewise, if our lower bound and upper bound of satisfaction are near 0 and far from the 95 percentile, we can say that we can guarantee that since the upper bound of satisfaction is less than 95%, the true probability of satisfying phi is less than 95%. And in the case where we have a wide satisfaction interval, say PL near 0 and PU near 1, we can't say either way where the true probability of satisfaction lies. It could be less than 95% or it could be greater than 95%. And in order to shrink this interval between PL and PU, we do have some options. We could first off collect more data in order to reduce our regression error. And likewise, we can try doing a finer discretization of the state space in order to reduce the uncertainties induced by that. So that is our framework in a nutshell. We started with a data set generated by our unknown system and an LTLF specification. And by adequately accounting for all of the uncertainties and by doing this formal abstraction, we can synthesize a strategy that has guarantees that actually extend to the underlying system, solving our original problem. So next up, I want to talk about some really cool examples that we have in the paper to highlight the efficacy of our approach. The first example I want to present is a linear switch system with Gaussian noise here. There are 3 control modes given by these A matrices. Each one of these control modes was learned using 200 IID data points using non-parametric Gaussian process regression using the squared exponential kernel. And the noise variance on the dynamics was 0 mean with 0.01 squared variance. This example is actually taken from related synthesis work with a state space that looks like this. The specification is given by not O until D, and the labels in the state space look like this, with O in the corner here and D's near the center of the state space. So given this, we partition up this state space in order to construct IMDP, and we run through our synthesis algorithm, and the result looks like this. So we ask for each one of the initial states in our discretization, is the probability of success greater than 95%? And if it is, we categorize it as Q yes and give it this light color, Q no gets this dark color, and all those indeterminate states end up with this light purple color. Now, clearly there's a fair bit of the state space where we are guaranteed with a minimum probability of 95% to reach D before we reach O. And intuitively, if we initialize the system in one of the O regions, we're going to violate the specification. Now, this simple example shows that while we can make pretty good guarantees on where we're going to satisfy the specification, we have some trouble with these indeterminate regions that might be overcome by collecting more data or perhaps doing some sort of refinement procedure in these regions. Now keep in mind, this was only with 200 data points, and we show that we can actually converge to better results as we increase the number of data points. The next example I'm going to present is a nonlinear switch system. In this case, we do assume a known form of the dynamics, in this case, just the previous state xk. The unknown part of the dynamics consists of one of 4 control modes, with each one being some nominal movement in one of the cardinal directions with some corrupting nonlinear term, either a sine or a cosine term. In the x1 component, the corrupting term depends on the x2 component, and vice versa. The x2 component depends on a nonlinear mapping of the x1 component. And this introduces just an interesting coupling between the 2 dimensions of the dynamics. And again, we do Gaussian process regression by now generating 300 IID data points for each one of these control modes. And the noise term here is Gaussian with variance 0.01 squared. Now the state space is a little bit different. The specification is a little more complex, given by globally not O, eventually D1, and eventually D2, with the partitioning in the state space looking like this. The D1 around the edges, D2 in the center, and O dispersed throughout. Now, by partitioning up the state space and using our GP regressions to construct the IMDP, we can run our synthesis algorithm to get this result. Again, the white regions correspond to regions where we can make guarantees on the performance of the strategy. The dark purple regions are those where we can make guarantees on the violation of the specification using the strategy. And Q question mark are all those regions where we can't make any rigorous guarantee about what's going to happen. In this case, we also have included simulation runs to demonstrate the efficacy of the policy, where the end without the symbol corresponds to the initialization of the system, and the end with the star corresponds to where it terminates. So in all of the situations where we initialize the system in Q yes, it takes a finite amount of steps before terminating and satisfying the specification. Likewise, if we start in Q question mark, one of 2 things can happen. The system can either find its way towards satisfying the specification, such as this example here, or the system applying the strategy will end up violating the policy. Now, as I mentioned previously, we do have some strategies in trying to shrink this Q question mark region. We could collect more data in order to reduce the regression error or do a finer discretization, but an interesting further research can involve identifying cases where maybe there are no choice of control actions in our unknown set that will result in satisfying the specification. Because it could be that the nonlinearities induced by this cross-coupling and these sine and cosine terms are just too much, so it's not guaranteed that a policy that satisfies the specification exists in the first place. In this work, we've developed a data-driven abstraction-based strategy synthesis framework for a switch stochastic system that has unknown dynamic components. And we can generate this strategy such that we still have guarantees that extend to the underlying latent system. And we do this by constructing this abstraction that formally accounts for all of the different uncertainties induced by the learning process and the discretization. There are a lot of cool things that I didn't get to talk about in this talk, including the optimal parameter choices in order to construct this abstraction, and also the challenge in using RKHS constants, which I'm currently working on more straightforward ways to bound these constants as well. A really exciting future extension to this work is taking this offline synthesis approach to the online setting, where we can hopefully account for situations like this that can arise. If we can collect more data online and update our abstraction online, perhaps we can expand the regions where we can make guarantees about our system. I've gotten the code validated that I've submitted for this conference, and I'm currently working on a more robust Julia toolbox that I can share with the community. So With that, thank you for listening. If you have any questions at all about this work, please feel free to shoot me an email here. And thank you so much for listening.